Okay, so what I want to do today is kind of talk about some of the stuff that we've been up to over at McGraw-Hill Financial. We've been, and just kind of give you where I'm going, I just want to hit, who we are, how we got FP in the door, the programming language that we wound up building in-house called Ermine, and what we've been doing for reporting, kind of building a DSL inside of our own, so building a language inside of our own language for describing reporting. And then what we're doing with open sourcing, what we're actively working on. So the exact opposite of the end note of the last talk. So who are we? I work for S&P Capital IQ, which is a division of McGraw-Hill, as a Standard & Poor's company. We have something like 4,500 customers, investment management firms, private equity funds, et cetera. We have a number of different products in sort of the data munging and quant space. In particular, the S&P Capital IQ platform is sort of a web-based front end for kind of getting at and kind of reading or manipulating just about any kind of information you want to know about the markets. And then ClariFI is sort of an installed Java toolbox for quants and traders who want to actually munge perhaps their own data in-house. Okay, and I'm not going to go too much into like kind of the back-end framework about like how all this is distributed across nodes. Most of that stuff kind of long predates the onset of the functional programming into the ecosystem. And so we're mostly concerned with being able to run kind of jobs on worker nodes, and the messages can get there. So how did we get FP in the door? So we were kind of, I guess before I arrived there, they were a very traditional sort of Java shop on one side of the house and a very traditional kind of C# .NET ecosystem shop on the other side of the house. So it's very much the antithesis of a where a Haskell developer expects to, or well, it's more where a Haskell developer expects to have to work, but not so much where he wants to. And so the kind of the tool that got us in the door were monoids, and I think they've been hit on a lot today. By lots of different people. So the next slide is perhaps a bit redundant. But the notion of a monoid is just that we have some kind of operation that we want to work with that is associative, and we have a unit for it. So we can define summation as a monoid and work with it directly. We can walk down a list, not really particularly caring which order we associated our way through the list. We could have chunked things up, passed them around, reduced individually, and then aggregated the results. Not rocket science, but it's a great parallel building block. One of the things that we use fairly heavily is kind of this just basic notion of a reducer. And so a reducer is sort of a monoid associated with some action that knows how to get a value into the monoid and what the heck I want to do with it when I'm done. This turns out to actually have a lot of structure to it. It forms a profunctor, a comonad, it's applicative. If you name a class, it's probably got an instance. It's actually a really powerful abstraction. Like this sort of reduce combinator down here. I don't know if I can point to it very well. Sort of captures the notion of a reducer can take a container full of values and give you back an answer. That comonad structure means that I can feed it multiple containers worth of values. There's many things that you can actually run with this. Now, the applicative that I mentioned in passing says that what I can do is, if one monoid is good, then two is better. So if I had two calculations that I wanted to perform, what I can do is I can just perform them at the same time. So simultaneously, I can run through my data set and mash it with one thing and mash it with the other thing. And then when I'm done, however I wanted to smash the answers together at the end, we can come through and say, reduce by one thing, take the answer from the other, and finish up by stitching them together. Okay? So now if we want to compute the mean, we do the sum and the length. Now we wouldn't actually do that because it's not numerically stable, but some people do. So we could also just do like num and fractional and make these actually pretty nice to work with. Like we don't see the wiring like hanging out of all of our code anymore. So this was sort of the tool chain that wound up in the door first, because long before I came on board, I gave a talk on using monoids and reducers at like Boston Haskell at one point. And a couple of guys here in the audience, I think, were there, Paul and Runar. And they went off and had to rebuild the performance attribution or portfolio attribution model that is used in-house. And basically, portfolio or performance attribution comes down to, you made money on your portfolio, why? And trying to figure out, like, was it by luck? Was it by skill? You know, it tries to break down the reasons why you're making money. And to do that, you wind up running a whole lot of different numerical passes over your data and chewing out just a bunch of different random numbers. Well, not random, hopefully. So the old implementation was implemented in Java, consumed all the memory on the largest boxes they could throw at it, had to have the entire data set in memory, and then it spat out results as serialized Java objects. And so Paul took the opportunity to go through and rebuild the whole system using monoids and reducers, sped it up by 2 or 3 orders of magnitude, made it now run in constant memory because it could run all the passes that it could simultaneously, do the couple that had left as cleanup passes after it was done. The new approach is easily extended. It's easy to drop new routines in. The code is quite readable. As I mentioned, drastic speed improvements. And then we concocted a bunch of combinators to actually enable us to flatten our results out to a database and express how we want to generate the schema pretty declaratively. I'm going to gloss over the fact that we have multiple Haskell algorithms. Well, actually, I didn't gloss over it. That we have to use iteratees sometimes because some things really need to go left to right. That there's some caching concerns and aggregating by sectors and dealing with missing data, et cetera, does make the story a little bit more complicated than the rosy picture I just described. But the general, it was still way better than what came before. The code was 10 times shorter and ran orders of magnitude faster. And so that turned out to be a pretty effective sales pitch for Scala to the enterprise. So at that point in time, they pretty much gave Paul freedom to do whatever the heck he wanted. And so now I'm there. So if I just pull out here, I think I can. All right, so I can pull up an actual report that's generated by this. And now this was generated by spitting it out to Excel. We can also run these things in a browser and on other platforms. And I'm going to talk about a bit of what we have that can generate these in kind of a cross-target manner using kind of the same specification across everything that we do. So we can spit out these, Brinson, attribution, templates, et cetera. And they have pretty charts, and in this particular case, in the Excel spreadsheet case, they hold all the data that they need to actually pivot and navigate through, like when you want to maneuver through the pivot table, the spreadsheet holds all the data it needs. If we're presenting it on the web, on the other hand, we want to go through and dynamically pull it out of the database in the back end that we need to answer the same. To provide the same front-end experience, we need a very drastically different interpreter for the kind of notion of reports that we have. So, let's see if I can resume. Hey, I remembered how. All right. So, this leads us to how the heck we generated that report, which wasn't a super sexy report, but it was the one I could grab really easily. So Ermine is a deliberate pronunciation of an Ermine, is our toy little functional programming language. And the easiest way to think of it is Haskell with row types. So it's not quite Haskell, but its main feature is that it's not Scala either. And so we started out writing a whole lot of Scala to run on the JVM. But really, writing functional programs in Scala is somewhat painful. To work with monads to get them to not blow the stack whenever you use traverse on a stream that's got more than 5,000 entries, you basically have to trampoline everything. So Runar wound up coming up with a nice trampolining monad for Scala Z, and we wound up building all sorts of tools for the Scala Z ecosystem, just in the process of just trying to get by day to day inside of Scala. So we decided we were going to write our own language, and we wrote it in Scala. So the implementation of this was originally built in Scala until the compiler tech just got to the point where we were spending more of our time fighting with Scala than we were improving our compiler. And so we started a new implementation of the compiler for Ermine written in Haskell itself. And then what we do is we compile down from Ermine to a portable core that we can then execute in Scala. Okay, and now Ermine itself as a language is somewhat interesting. It has a very strong type system. It has a novel form of row types that I'm going to talk about a little bit. And it has polymorphic and constraint kinds because, well, they were coming into GHC at the time and I wanted to understand how they worked. It has just enough rank n type support to be dangerous. It implements it by the dumbest algorithm possible. No offense to Dan if he's in the audience. HMF is a really simple way to get rank n types in your language if you actually have to implement something and you don't know how to do it right. Well, if you don't know how to do it in a way that doesn't require extra annotations and stuff. It was really easy to get right. And it fits our domain. We were able to just bake in database support into the language all the way down. We have support for notions of fields and tables as kind of primitive notions. We can expose it to our end users because we own it, we trust it. We can define our own notion of what is safe to compute. We have, like, in-house, one of the user interface guys went off and prototyped a structured code editor that, like, can only generate, like, type-safe, like, type-correct code as you're typing and stuff. So if we really have to expose this to an end user, you know, undefined is going to come at the top of every list if we leave it in scope. But they'll at least only be, somebody wanted something, that becomes an awful lot of engineering effort for us to just have to deal with every random permutation that somebody wants to do or just say no and piss off a client. So it would actually be really nice if we could just turn around and give them the tools to do it themselves for the 5% that are expert users, and to enable our, like, support staff to go off and build a lot of the solutions that we don't want to be spending all of our time on in development. So that was kind of the original motivation for bringing Ermine into existence. I actually recall being kind of vehemently opposed, and then I was a consultant at the time, and then went away. And so Runar decided he was just going to implement it. And so, you know, completely, you know, like based on like a napkin sketch of a type system that I gave him, like just went off and decided he was going to write a compiler, and it worked. And so we wound up with Ermine, because, you know, existence has a lot of power in terms of shaping future behavior, and we've been tinkering with it ever since. So what I want to talk about a little bit is just the notion of row polymorphism that we provide inside of Ermine. And so row types are a really powerful tool for describing, like, records that can have or lack a field. If you ever wanted to, like, work with, like, a record type in Haskell or something like that, and you just, you know, I just want to set the foo field. I don't care what other fields it has. You know, I want to set foo equal 12 and want to talk about that type. OCaml has this notion. There's lots of languages that have some, you know, ML polyr was actually the one that we were looking at the most closely. Matthias Bloom has a nice project. And Mitchell Wand, I think, is he floating around here, has a old type system for playing with row types. And Harper and Pierce have one that has a checking algorithm, but not an inference algorithm. And so, but we really wanted something that we could do type inference on. And so we literally just kept throwing scribbles on a piece of paper until it seemed to be confluent. We've not actually bothered to do the full proof. It works for the situations that we've encountered, and we haven't had to spackle it in a long time. But it works. So if we go back to like just the traditional way that these things are denoted, is we would usually say that like we want to have, if I wanted to const some field onto a record, I want to be able to actually add a missing field to a record. Then I can say that const of some field L onto a record that lacks L, that's the slash there, it, takes an A, and in this case, I think I screwed up my notation. That should be curly braces around the bracket R. It's going to take an R and give me a record where it's R extended by L with type A. And then we can talk about tail as being, drop L off of this thing. So take a record that has L of type A and give me R. Now, these things are associative, so things can move all over the place. Unification goes a little bit nuts. You have to be careful. So we move most of this reasoning into the constraint system. But if you look at something like the type of join here, and I'm going to use this kind of funny bracket dot dot syntax to denote a relation. So that's so join is going to take a relation with fields R and join it with a relation with fields S, doing a natural join. So wherever the fields agree, they're going to mash them together and give me a relation R or S. This would be, I think, Harper and Pierce probably had that notation, or something close to it, if I didn't bastardize it too much. Now, the problem with this is that inference flows strictly unidirectionally through join. It kind of flows from the arguments to the result. And so there isn't okay. Sorry. Don't have my glasses on. So there isn't much ability to, like if I know R and I know the result type, if I know the result join, I don't really get to know, well, then this other thing can have or may not have some of the fields. And it gets really tricky to start communicating between has and lacks and subsumes when you start talking about inference. So what we did was, Paul came up with this trick. That way I'm blaming Paul in case it goes wrong. Is that we can use a single constraint type, which is that we can say that we can partition the row A into field sets B and C. Okay, and this is K, or you can pass it however many things you want to partition it into. Okay, and then join now has the type that we're going to work with new row types D, E, and F, such that D can be partitioned into A and B, and E can be partitioned into B and C, but F can be partitioned into A, B, and C. And that can be partitioned into uniquely determines the results as much as we need. And so now when you actually start working with these joins sort of in anger, if you know some of the properties of one of your inputs and some of the properties of the other of your inputs, you can infer more of the properties of the results, and you can infer backwards through joins rather than just have the information accumulate outward. So if we had only really wanted to accumulate outward, we could probably have gotten away with just doing it with something with HLists inside of Haskell. But then we would have been accumulating results for a long time. Now, so some other quirks of the language. In order to express all the types that we want to work with these relation types, and to meet kind of the requirements of working with HMF, I need to know that everything on the right-hand side of the double arrow in Haskell is in a canonical form. I have to pick an ordering for the variables in order to use HMF. So as an artifact of the way that we chose to implement rank n types, we're kind of forced into this. And so like if you looked at monad state SM, the S variable doesn't occur on the right-hand side of the colon equals. or the equals, the of the constraint. So, so to work around that, to work with HMF, one of the things that we do is that we enable us to lift variables that don't occur on the right-hand side into the left-hand side. And this is a perfectly legal, logical transformation if you view it from an implication standpoint. All I'm doing is saying instead of for all S and for all M, there exists an implication. I can say there exists an S, so I can pull it in. Now, when we start talking about has and lacks constraints, then A having B is saying that A can be partitioned into B and something else, where C could be the empty set of fields. And A being disjoint from B says that C can be partitioned into A and B. So it just says that there exists some C that I can partition it into, that I can partition into these two things. And so that gives me a notion of disjointness and a notion of has, and the notion of disjointness subsumes the notion of lacks, because B can now be multiple fields or one. And so that gives us the notion of row polymorphism that we work with. And I'm not going to show the type system for it. So with that, what we have is a desire to actually use this for end users, because that's how they keep paying us. And I just lost my screen. Hold on. Come on. Flickered. All right. Oh, hey, check it out. All right. And ding. Hey, I resumed twice. Great. Okay, so to motivate or to actually get them to keep paying us. With Ermine, we built this reporting framework. And the idea of the reporting EDSL that we have is that we have this whole relational algebra combinator set that we were using to talk about joins and all these sorts of things that let us build up a sort of declarative specification of how we want to get our data from our different data sources. And so we can now push that down and execute it directly on SQL Server or in Vertica, or inside of our security master, which contains all the information that we want about securities, which has its own API, or off of our data cache server, which does this other completely different API. So we have one kind of declarative specification for how to do all the relational algebra operators that we want, and we can push it down as close to the data source as we can, and we can do the rest of the munging inside of memory, if need be, and we can push tables back and all that sort of stuff. Then on top of that, what we have is another EDSL for talking about building reports. Okay, and so we can spit out, pretty little layouts involving pie charts and superimposed various charts that can render in a pretty consistent manner across a lot of different targets. Okay, using whatever alternate interpretation techniques that they have to make sense on those individual platforms. Okay, and the code itself won't win any awards. This was actually written by a non-functional programmer. Well, he's functioning, but a programmer who had never written a line of functional code in his life before he started working with us. And so we were able to actually grab a couple of guys who'd just done Java, some user interface stuff here and there, and get them to understand this stuff. So it's not impossible. It can be done. It required a little bit of hand-holding here and there to get them through some of the more Baroque type errors. I mean, we are talking about a DSL inside of a custom language that's being developed as the guy is facing his issues, right? So he has to have an awful lot of faith in us to know that when we yell at him that it's or when the type checker yells at him, that it's really him. But overall, this is a very declarative specification for what a report looks like. We're saying, hey, we have some drop-down, and it's going to use a remote choice of the date range, using whatever the reporting ranges are for this report ID. And we're going to get, there's a little lambda there. I'm actually fudging the syntax to make it a little more Haskell-y so that somebody in the room can read it. And we're grabbing the drop-down itself and the notion of the selector that we can actually use for saying when we want to trigger on events. And so what we're doing is we're kind of building up this document that happens to have inside of it kind of these regions that are saying this region depends on this value from this lookup, or this drop-down user interface choice. Okay. And so here what we've got is I've built the drop-down, and then I've put the drop-down inside of this like H-flow of content on the screen. Okay. And then down here I said this box is using the value from that date range selector, which is this value, and now I can go through and actually make use of the actual meaning of that value. Okay. So this report specification is write once. We can, it's not really, but it's pretty close. What we tend to do in practice is we tend to, in order to not have to support just the intersection of the functionality of all the platforms that we support, we tend to write combinators that describe parts of reports and then stitch them together into a final report for each target. Or in some cases, we can get away with using one report across all, when the intersection is enough to describe what we want and the customer isn't screaming for more. But it is still, it's a pretty straightforward specification. We're not dropping into imperative la-la land. And so we can take this report and run that same report that I loaded up earlier. This would be running it inside of Swing GUI. We can also render it out to HTML as an HTML plus AJAX kind of application, so that just the portion of the page that got changed actually has to refresh. It's not the full page every time you submit back. It actually feels really punchy and interactive. The charts, like if you're looking at a table, we can scroll that thing, fetching the data via AJAX style techniques so that it's just the window that you're looking at that we actually had to load. We don't have to load 1,000,000 records in order to show you 1,000 or 100 or, well, hopefully don't have a screen that can show 1,000 records. We can dump it out to Excel. When we have to send it to Excel, we can take all of the data that we need to support the query, put it in the document itself, and then build a pivot table inside of Excel to ape the sort of legend and the tool chain that we wanted to expose. The user experience we wanted to give can be presented, even though it's a vastly different interpretation mechanism. With PDF, we're doing the same kind of CSS styling that we use. We actually wind up borrowing parts of the HTML writer to implement the Swing writer so that we can get consistent styling. So we can use just web widgets inside of an embedded Swing GUI if we need to patch over something. But for the most part, the majority of the GUI is native Java all the way down. You can write portions of your report in Markdown, and we have all sorts of nice little toys to make it actually user accessible. So that's it. How am I doing? All right, so good, because all I'm going to talk about is that we've open sourced the code that we've got for almost everything that I just showed you, except for the reporting framework, unfortunately. So the old Scala implementation of Ermine is available. We're not really extending it. It's there. We gutted out a few of the reporting pieces, got it to build. You can actually load it up, sit at the REPL, play with row types. And it's actually pretty fun to hack around in. And it's a good preview of where we're going. The new Haskell version isn't done yet. It is something that we're actively working on. And there's a Ermine IRC channel on irc.freenode.net of people who are interested in hacking on it and have been kind of giving us active feedback as we go. We're trying to get to the point where we can more actively use community effort. We have a new core interpreter. Now that we have the separated Haskell version, we're compiling down to this fairly portable core. And so we have the core interpreter for that online. And while we do not have the reporting framework online, what we do have is JMacroRPC, which Gershom Bazerman implemented, which was actually sort of the work in, like, as we described what we wanted it to be, Gershom went off and prototyped it all in Haskell inside of his existing JMacro library and sort of exposed it to the world. So there is a version of, at least for like the HTML side of the kinds of things that we build, can be had, and it's open source and it's on Hackage and can be used today. So that's all I've got. It's either good or really bad. Yes.
So have you managed to roll it out to a lot of users, or is it still some friends?
So we're currently using it on the main S&P Capital IQ website for portfolio attribution, and what else are we doing it with?
We have one web page on the